In early October 2025, Mars passed through a region of space unlike any it had seen before. For a few days, faint traces appeared in the data, minute fluctuations in light and motion, subtle enough to escape the eye but not the instruments orbiting the planet. The Trace Gas Orbiter, quietly circling above, recorded a sequence of images from its Cassis camera, barely visible dots shifting across a black background, nothing dramatic. No glowing tails or bright impacts. Yet those frames marked something historic, the moment when fragments from an interstellar object crossed the vicinity of another planet for the first time. At the time of closest approach, on October 3rd, the main body of the object passed roughly 30 million kilometers from Mars, but the story didn't end there. In the weeks that followed, scientists began watching the data more closely. By October 30th, as the object neared 1.4 astronomical units from the Sun, models predicted rising activity, jets of gas, and heat-driven outbursts, capable of releasing new fragments into interplanetary space. Each of those fragments could follow slightly different trajectories, some intersecting Mars's orbit days or weeks later. No one can yet say which particle, if any, will reach the planet first. But in that uncertainty lies a question that connects astronomy, physics, and chance itself. What hits Mars first? Tonight, we embark on a new journey where the theme of 3I Atlas fragments, what hits Mars, first appears not only as a scientific phenomenon, but also as a question that challenges our imagination. If you enjoy this kind of quiet, long-form storytelling, if it helps you learn, focus, or simply relax at the end of a noisy day, take a moment to like the video and subscribe, but only if this space truly brings you peace. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the tented world. Because now, the clock ticks toward October 30th, when 3I Atlas will meet the Sun head-on. Somewhere between those days and the red planet's sky, an answer is forming hidden in a stream of dust, ice, and invisible motion. The question remains, when the fragments of 3I Atlas finally make their crossing, what hits Mars first? If the interstellar object designated 3I Atlas undergoes disintegration along its trajectory, the first material to grace the Martian atmosphere may not be a singular, macroscopic rock. Instead, a vanguard of ultrafine dust, particles laden with carbon dioxide, ice, and accelerated by radiation pressure, could be propelled ahead of the main nucleus. This microscopic debris, a silent herald from the depths of interstellar space, would initiate the encounter not with an impact, but with a whisper. According to current models of cometary outgassing, radiation forces from our Sun are more than capable of segregating dust by size and composition, creating an extended stream of precursor material. But what if the composition of this dust holds a more volatile secret than our own solar system's comets? Data from the James Webb Space Telescope and the Swift Observatory's UVOT instrument, collected between late July and mid-August, revealed an anomalous coma rich in carbon dioxide, with a carbon dioxide to water ratio of approximately 7 to 8. This suggests a nucleus whose activity is powerfully driven by carbon dioxide, even at great distances from the Sun, a stark contrast to solar system comets. Some of this escaping carbon dioxide ice, mixed with carbonyl sulfide, could form not solid grains, but porous, fragile structures akin to microscopic glass foam. As these delicate particles encounter the thin upper atmosphere of Mars, traveling at immense interstellar velocities, they would not merely ablate. They would detonate in a series of microscopic explosions, each a minuscule release of energy. Could such insignificant events, multiplied by trillions, collectively weave a shroud around an entire world? This leads to a speculative hypothesis. These micro-explosions could inject a fine, ionized metallic dust into the high thermosphere, generating a tenuous, global cloud that envelops Mars. It would not be a brilliant display, but a faint, persistent interstellar haze, a ring of mist from another star. The analysis of such an event unfolds across escalating levels of consequence. At its most benign, it would manifest as a faintly luminous micrometeoroid shower, a phenomenon almost imperceptible to all but the most sensitive instruments. A moderate scenario would see the formation of a temporary, localized layer of metal ions, subtly disrupting the Martian ionosphere and providing a novel subject for study by orbiters like the Trace Gas Orbiter and MAVEN. Yet, in an extreme case, should a significant outburst of dust precede the main body, this interstellar fog could persist for days, a lingering atmospheric anomaly. What transient signatures would such a veil leave upon the tenuous Martian sky, and would they be mistaken for a natural seasonal phenomenon? The potential atmospheric infusion presents a unique natural experiment. It offers a pristine window to observe and measure genuine interstellar dust grains colliding with a rocky planet, a calibration point for impact models that protect not only our assets on Mars, but also inform our understanding of similar threats to Earth. The risk to orbital assets is considered minimal, a calculated trade-off for the scientific windfall. This is not a cataclysm, but an opportunity, a chance to sample the building blocks of another system delivered to our observational doorstep. But if this dust is so fundamentally different, what other, more reactive compounds might it carry, and what long-term, cryptic chemistry could it initiate in the Martian environment? The timeline for this potential dust interaction is not a matter of the close approach itself, but of the conditions established in the preceding days. The golden window for modeling this event opened on the 3rd of October, when the Trace Gas Orbiter's CASSIS instrument successfully captured the object's motion against the star field. At a distance of approximately 30 million kilometers, this was not a detailed portrait, but a crucial data point, a single frame in a cosmic tracking shot that defines the initial state of the debris field. This single observation provides the boundary condition for every subsequent simulation of fragmentation and dispersion. Without this foundational measurement, any prediction of the dust front's arrival would be mere speculation. The Mars Express orbiter, with its shorter exposure time of half a second, failed to obtain a clear image, underscoring the challenge of observing such a faint and fast-moving target. This contrast between the successful TGO observation and the unsuccessful one highlights the precision required to track these interstellar visitors. The CASSIS data transforms the passage of 3I Atlas from a mere astronomical event into a quantifiable physical process. It allows us to project the cone of possible debris trajectories forward in time toward the moment Mars passes through that ethereal stream. The stage is now set, the initial conditions locked into our models. As we await the object's perihelion around the 29th and 30th of October, we are left to ponder. What other secrets will be revealed in the flickering data streams from our robotic sentinels at Mars? And will the first touch of another star system be recorded as a gentle global rain of light? The golden window opened on the 3rd of October, 2025, a precise and fleeting moment in the celestial mechanics of the inner solar system. It was the instant the interstellar visitor, designated 3I Atlas, transited the orbital plane of Mars, a mere 0.19 astronomical units from the red planet. This alignment was not merely a geometric curiosity, it was an opportunity, a keyhole through which humanity could peer at the stranger passing by. The European Space Agency's Trace Gas Orbiter, a sentinel circling Mars, turned its sophisticated CASSIS camera towards the predicted coordinates. On the 7th of October, the agency released the data, a sequence of images, a 5-second exposure that captured a faint, mobile point of light against the star field. From this brief glimpse, astronomers could calculate an angular velocity and discern the faint, diffuse glow of a nascent coma. The Mars Express orbiter, with its different instrumentation and shorter exposure times, saw nothing, a null result that only served to highlight the specificity of the conditions required for this observation. The data confirmed the closest approach had occurred days prior, at a distance of approximately 30 million kilometers. According to current models of cometary behavior, even an interstellar object would begin to exhibit activity as it approached the warmth of the Sunday. The faint coma detected by the trace gas orbiter aligns with the expectation of volatile ices sublimating from the object's surface, creating a tenuous cloud of gas and dust. The velocity and the morphology of the coma are consistent with a small, rocky, icy body responding to increasing solar insolation. Scientists suggest this could be due to a localized jet of activity, a small fissure on the surface, venting material into the vacuum of space. The data provides a valuable anchor point for understanding the object's rotation state and initial mass loss. Yet, the very nature of this data, a short sequence of images, a visual GIF, invites a deeper inquiry. Does this sequence represent merely a passive observation, or could it be something more, a temporal marker for an event whose consequences were yet to unfold? The speculative hypothesis posits that the GIF from the European Space Agency was not just a picture, but a space-time anchor for a subsequent, more diffuse phenomenon. The faint coma, a cloud of microscopic particles, was not a uniform shell but a structured stream. As 3I Atlas moved along its hyperbolic path, it left behind a tenuous trail, a river of interstellar dust flowing through the interplanetary medium. The gravitational pull of Mars, and its position at that golden window, could have acted as a lens, focusing this sparse stream. We can analyze this concept across escalating levels of intensity. At its most conservative, this would manifest as a sparse blade of dust, a gentle rain of microscopic particles intersecting the Martian orbit days after the object's passage, perhaps detectable only by the most sensitive instruments on the orbiters or rovers. At a moderate level, the outgassing may not have been uniform, but pulsed, releasing 2 or 3 distinct packets of dust that would arrive as separate, faint waves. But the most extreme interpretation involves the physics of radiation pressure. The minuscule beta parameter for these dust grains, the ratio of radiation pressure to gravity, could have sculpted the cloud, focusing the smallest particles into a convergent beam. This would create a brief but pronounced meteor shower in the thin Martian atmosphere, a silent, brilliant streak against the alien sky, a ghostly echo of the visitor's passage. If the GIF was the starting pistol, was the Martian sky about to witness the race? This data from the golden window immediately became the critical boundary condition for every Monte Carlo simulation of debris dispersion. The observed position, velocity, and coma brightness at a known time and location provide the initial state from which millions of potential particle trajectories can be calculated forward and backward in time. It offers a rare chance for immediate verification. Should any anomalous dust, flux, or atmospheric meteoric event be recorded by the fleet at Mars in the subsequent days, it can be directly correlated with this model. The hypothesis can be tested not in years, but in hours. The GIF, therefore, transforms from a simple record into a predictive tool. But what forces would govern the production of this dust? The visitor was now falling closer to the Sun, and the quiet activity observed at Mars was merely a prelude. What would happen when the solar furnace was turned to its full intensity? As 3I Atlas continues its journey, it approaches its perihelion on the 30th of October, 2025, a close encounter with our star at a distance of approximately 1.4 astronomical units. This is the moment of truth, the point where thermal and hydrodynamic accelerations could flip a switch deep within its core. Conventional cometary science predicts an outburst, a massive increase in dust and gas production as subsurface ices are violently exposed and sublimated. This would generate a new, far denser stream of particles, a river that could swell into a flood, The geometry of its path suggests this new stream could intersect the orbit of Mars mere days or weeks after the event. The brief, silent gift from the golden window may have been the first, faint whisper of an object learning to speak. The outburst at perihelion could be its first true shout, a declaration of its presence that will echo across the solar system. Will the instruments at Mars be ready to listen, and will they understand the message carried on the solar wind? The approach of Comet 3I Atlas toward perihelion in late October 2025 presents a critical test for our understanding of cometary thermodynamics. At a distance of approximately 1.36 to 1.4 astronomical units from the Sun, the solar flux becomes sufficient to trigger a profound transition. The dominant volatile frozen carbon dioxide stored in the nucleus does not merely melt, it sublimates with explosive efficiency, transitioning directly from solid to gas. This sudden, massive release of pressure acts as the primary engine for an outburst, potentially ejecting vast quantities of dust and gas in a fan-shaped plume, directed both toward the Sun and away from it. A paradoxical push against the very radiation pressure that enables it. Could this be the moment the hydrodynamic thermal acceleration process flips a switch, initiating a cascade of fragmentation? The mainstream scientific explanation posits a predictable, if vigorous, cometary outburst. According to current models, the heat penetrates the comet's porous crust, reaching subsurface reservoirs of carbon dioxide ice. The resulting gas builds up in subterranean pockets until the overlying structural strength is overcome, violently venting into the vacuum of space and carrying entrained dust particles with it. This is a known phenomenon, observed in other carbon dioxide-dominated comets, where the release acts as a natural pressure valve. Scientists suggest this could be due to the unique thermal properties of carbon dioxide ice, which sublimes at a much higher temperature than water ice, allowing it to remain dormant until a specific, critical solar distance is crossed. Yet, does this conventional model fully capture the potential for a chain reaction within an interstellar object of unknown structural integrity? A more speculative hypothesis envisions a far more dynamic and structured event. Imagine not a simple rupture, but the uncorking of a pre-existing smoldering network of carbon dioxide vents. As the main seal breaks, it does not simply release gas. It fires a sequenced volley of icy bullets, fragile, porous aggregates of ice and dust resembling cosmic cotton balls. Each of these projectiles would itself be a miniature comet, briefly venting its own volatiles as it tumbles away from the nucleus, creating a cascading, multiplicative ejection. This would be less a single explosion, and more the activation of a complex, geologic plumbing system finally reaching its tipping point. What if the comet's interior is not a homogeneous mix, but a fractured landscape of pressurized cells waiting for a trigger? The data already in our possession lends credence to an event of significant magnitude. NASA's trajectory calculations confirm perihelion will occur around the 29th to 30th of October, 2025, at precisely this volatile distance of about 1.4 AU. More critically, observational data from the James Webb Space Telescope's near-infrared spectrograph, collected in August and September of 2025, has confirmed a coma exceptionally rich in carbon dioxide. The ratio of carbon dioxide to water is among the highest ever recorded in any comet, strongly suggesting that the carbon dioxide engine will be the dominant force immediately before and after its closest approach to the Sunday. Does this extreme chemical composition precondition the comet for a uniquely violent performance? Our analysis must therefore consider a spectrum of possible outcomes, each with escalating consequences. At its most benign, level 1, we would witness a gradual, sustained increase in dust production, a gentle brightening of the coma that provides valuable data on particle size distribution and the mechanics of radiation pressure. A moderate, level 2 event would involve a sharp, 1 to 2 day outburst, propelling a cloud of high beta particles, dust grains so small and light they are strongly pushed by solar radiation. This ejector would cross the orbit of Mars within 3 to 10 days, offering a fleeting opportunity for in situ analysis. But what if the reality aligns with the extreme Level 3 scenario? In this most dramatic hypothesis, the outburst is not a surface venting, but a fundamental fragmentation of the outer shell. The release of internal pressures is so violent that it shatters a significant portion of the nucleus, generating not a diffuse cloud, but a dense, sequential chain of dust filaments. This debris field would not simply cross the Martian orbit, it would momentarily inhabit and sweep through the entire Hill sphere of the red planet, a region where its gravity holds sway. This presents an unprecedented opportunity. The fleet of orbiters, notably MAVEN and the Trace Gas Orbiter, would be perfectly positioned to act as real-time sensors within this artificial meteor stream. They could directly measure the drag coefficients and radiation pressure effects on this exotic dust, allowing us to refine and calibrate our models of non-gravitational forces with empirical data. But if the comet can shed its skin so readily, what does that imply about the fundamental cohesion of interstellar objects? This leads us to a final, contemplative point. The hyperbolic, interstellar trajectory of 3I Atlas poses absolutely no threat of a direct collision with Earth. For Mars, the risk is not from a large impacting body, but from the subtler, more pervasive effects of a micrometeoroid shower. The high-velocity dust, if sufficiently abundant, could cause transient ionization in the upper atmosphere, creating a form of artificial meteor shower detectable by our instruments. Yet, this very absence of a catastrophic impact warning allows us to observe the event with scientific detachment, to see it not as a danger, but as a natural experiment of the highest order. As we watch this celestial visitor react to our Sun, we are left to ponder, if there is no warning for a major collision, could the true message be written in the dust itself? The trajectory of the interstellar visitor designated 3I Atlas was, by all terrestrial measures, a perfect celestial miss. Orbital dynamics calculations, refined by radar pings from the Goldstone Deep Space Network and optical tracking by the Vera-C. Rubin Observatory placed its closest approach to Earth at a comfortable 1.8 astronomical units. There would be no catastrophic impact, no extinction-level event triggered from the void. The danger, it seemed, was not in the bulk of the object itself, but in the ethereal wake it left behind. For Mars, however, the encounter was far more intimate, a close pass of merely 0.19 astronomical units, and the primary concern shifted from impact to a more subtle atmospheric phenomenon, a potential ionospheric dust rain. From a mainstream scientific perspective, the interaction between a comet's dust, tail, and a planetary atmosphere is a known, if not fully quantified, process. As a comet approaches the Sun, solar radiation pressure and outgassing propel countless dust particles away from the nucleus, forming the extensive sweeping tails that have captivated humanity for millennia. When such a tail intersects with a planet, the results can range from undetectable to spectacular. Scientists suggest this could be due to the ablation of fine-grained particles in the upper atmosphere, a process that injects free electrons and ionizes metallic atoms like sodium and iron, potentially creating weak, transient layers of enhanced plasma. According to current models, the tenuous atmosphere of Mars, with a surface pressure less than 1% of Earth's, offers little resistance, allowing these micrometeoroids to penetrate deeply before vaporizing in a final, luminous flash. The CASSIS camera aboard the Trace Gas Orbiter was tasked with monitoring such events, though its targets were typically 10 to 100,000 times brighter than the faint, diffuse glow anticipated from 3I Atlas's dispersed coma. Could the instruments even perceive the whisper of this interstellar dust? But that does not account for the unique composition of an object born around another star. The speculative hypothesis introduces the possibility of a violet rain in the upper Martian atmosphere. This would not be a downpour of water, but a cascade of energy, as the fine, uncharacterized dust from 3I Atlas, a dust whose mineralogy is entirely alien to our solar system, plunges into the thin air. The intense friction would not merely heat it, it could excite the atoms to a state of profound energy. Hydroxyl radicals, common in cometary comas, and ionized metals from the dust itself, might be driven to emit light not in the familiar green of oxygen or red of nitrogen, but in a dominant, haunting band of violet. The Martian night sky, for a brief period, could be subtly illuminated by an otherworldly aurora, a chemical signature written in a color palette foreign to our own experience. What spectral lines, unknown to our periodic table, might be hidden within that faint purple glow? We can analyze this potential interaction through a graded series of escalating consequences. The first level is benign, a mere whisper of an event. In this scenario, the dust grains are sparse and fine, their ablation producing a transient, minor increase in the population of hot electrons within the Martian ionosphere. Instruments like the MAVEN orbiter would register a slight perturbation in local plasma density, a brief spike on a data graph that would be noted, studied, and filed away. It would be a minor curiosity, a data point in the long-term study of atmospheric chemistry. Is this the most we can expect from an interstellar handshake, a barely perceptible static charge against the Martian sky? The second level intensifies the phenomenon. Here, the dust density is greater, and the particles are of a composition that leads to more vigorous and sustained ablation. The result would not be a uniform sheet of light, but a patchwork, a spattering of faint, luminous spots across the upper atmosphere. These would be weak airglow events, localized and fleeting, potentially visible to sensitive cameras in orbit. They would represent a direct, visible transfer of material from an interstellar object to a planetary body within our solar system. Each glowing dot would be the final, fiery testament to a grain of dust that began its journey around a star we have never seen. Do these isolated flashes of light represent the burning archives of a distant planetary system? The third, most extreme level ventures into the territory of a micrometeoroid storm. If the dust tail of 3I Atlas were particularly dense with particles just large enough to survive deep penetration, the cumulative effect could be a localized, temporary disruption of the Martian ionosphere. The constant, fine rain of ablating material would create a turbulent, ionized patch in the atmosphere. This could act as a natural shield, or more accurately, a source of interference, scattering and distorting the solar wind particles that normally bathe the planet. MAVEN's sensors, designed to measure the pristine flow of the solar wind and its erosion of the Martian atmosphere, would instead detect a chaotic, localized turbulence. This would not be a global event, but a temporary intense microstorm within the planet's magnetic and atmospheric environment. Could such a transient, dust-induced squall inadvertently teach us how to artificially engineer a protective buffer against stellar radiation? The practical implications of this dust rain are a study in contrasts. The risk to orbital assets like the Trace Gas Orbiter or the MAVEN spacecraft is negligible. The particles are too small to cause significant physical damage. The scientific opportunity, however, is immense. Mars presents a unique laboratory, an atmosphere too thin to quickly burn up small particles yet thick enough to record their interaction in exquisite detail. Observing this event provides a pristine dataset on dust-ion interactions in a thin, carbon dioxide-dominated atmosphere, a process fundamental to planetary science, but rarely observed from its very inception with material of a definitively extrasolar origin. We are being offered a front-row seat to a process that might be commonplace across the galaxy. But if this is the gentle rain, what might the leading edge of the storm, the vanguard of finer particles, have already delivered? Indeed, before the main body of the coma and its larger fragments ever drew near, a more subtle and swift precursor would have arrived. Pushed ahead by the relentless pressure of solar radiation, the sub-millimeter to millimeter-sized dust grains, possessing a high area-to-mass ratio, would have experienced a significant radial velocity component known as the radiation pressure beta effect. These tiny fragments, some potentially encased in or containing frozen carbon dioxide, excavated from the object's interior, would have raced ahead of their larger siblings. Their relative drift velocity could be substantial, making them the first ambassadors of 3I Atlas to kiss the Martian atmosphere. If the comet's nucleus had undergone any fragmentation events, a common fate for such bodies, the release of these small, fast-moving particles would have been greatly amplified. They would be the scouts, the initial skirmish line in this cosmic interaction. What chemical surprises might these sub-millimeter vanguard particles, carrying the frozen breath of an alien world, impart as they disintegrate high above the red plains? The silent vanguard of the cometary disintegration does not arrive as a singular, cataclysmic impact, but as a whisper. In every fragmentation scenario, the sub-millimeter dust grains, those motes of silica and complex organics, are the first to feel the subtle, unceasing push of solar radiation pressure. Possessing a high beta parameter, the ratio of radiation pressure to gravitational force, they are relentlessly accelerated away from the main debris field, becoming the spearhead that will first touch the Martian environment. These are not the dramatic, fireball-producing projectiles of legend. They are a faint, ethereal haze, a precursor cloud, driven by the physics of light itself. According to current models, this initial influx would be a gentle rain, a statistical increase in micrometeoroid flux that would barely register against the background noise of interplanetary dust. But what if this initial whisper carries a message written not in rock, but in ice? A speculative hypothesis presents a truly enigmatic possibility. What if these vanguard particles are not mere flecks of silicate dust, but intricate microballoons of frozen carbon dioxide, cloaked in a thin, dark mantle of cometary dust? This invisibility cloak of silica would protect the volatile core during its journey, allowing it to survive the transit and plunge into the Martian upper atmosphere intact. At altitudes between 80 and 100 kilometers, the fragile balance would shatter. The frictional heating, minimal for such small particles, would nonetheless be sufficient to trigger the sublimation of the carbon dioxide ice in a rapid, silent burst. The dust mantle would disintegrate, and the particle would vanish, not in a flash of light, but in an instantaneous transition from solid to gas. This would leave no burning streak in the sky, only a subtle, localized enrichment of the atmosphere, with carbon dioxide and a fine, suspended dust. Could the very first sign of the comet's arrival be an atmospheric chemist's anomaly, rather than an astronomer's flash? Data from the James Webb Space Telescope and the Swift Observatory lend a curious, if indirect, credence to this notion. Their spectroscopic analyses of the comet's coma in the months leading to the encounter have consistently shown a carbon dioxide-dominated activity, far outpacing the outgassing of water ice. This preponderance of carbon dioxide suggests that the non-gravitational forces altering the comet's orbit are driven by this very volatile, and that a significant fraction of its ejected mass could indeed be in the form of carbon dioxide ice grains. Furthermore, the precise orbital geometry following the October 3rd flyby allows for a fascinating dynamical effect. High beta particles, once freed from the comet's nucleus, are not only pushed outward by radiation pressure, but can also have their orbits perturbed and tilted. This radiation-driven nudging could alter their trajectory just enough to cause an earlier intersection with the sphere of Martian gravitational influence, shortening their travel time and ensuring they are the first to arrive. Is the timing of this ethereal rain not just a function of speed, but of a celestial reorchestration conducted by sunlight itself? We can analyze this initial contact through a graduated lens of intensity. At its most benign, level 1, The influx would be a sparse shower of a few thousand particles per second per square meter, a signal so faint it would require the most sensitive detectors on orbiting spacecraft like MAVEN to discern it from the usual background. It would be a ghostly signature, a statistical murmur in the data. Is this subtle augmentation the true beginning of the event, or merely the prelude to something far more substantial? Escalating to level 2, the cometary stream begins to deliver a more pronounced downpour. For hours, a sustained rain of micrometeoroids would pepper the upper atmosphere, a prolonged event that would create a continuous, if diffuse, layer of ablated metals and injected vapors. This would no longer be a mere curiosity for atmospheric scientists, but a significant perturbation to the ionospheric chemistry. How long can an atmosphere remain stable under such a persistent, if gentle, bombardment? The most extreme scenario, level 3, envisions a thin global curtain of dust enveloping the day side of Mars. While optically thin, this permanent shroud would subtly alter the albedo and act as a distributed site for complex photochemical reactions high above the surface. It would be a planet briefly wearing a veil woven from the essence of a comet. What long-term climatic echoes would such a transient veil produce? The imperative, therefore, is clear. To capture this elusive vanguard, the MAVEN orbiter must be positioned as the primary sentinel. Its high-resolution plasma and neutral gas sensors must be tasked with a dedicated observational campaign in the 1 to 2 weeks immediately following October 3rd. Operating in a targeted high-cadence mode, it could sniff out the telltale isotopic and compositional signatures of the sublimating carbon dioxide, microballoons, and the accompanying dust. This would transform a theoretical prediction into a measurable phenomenon. But if this is the vanguard, what form will the main body of the army take? For the story of this cometary encounter does not end with these microscopic pioneers. The laws of orbital mechanics dictate that they are merely the scouts, the outriders for the slower, more massive fragments that follow in their wake. This leads us inevitably to the delayed arrival of the larger fragments, the ones measuring from centimeters to meters across. These are the laggards, the ponderous followers whose greater mass grants them a higher inertia and a much lower beta parameter. They are virtually immune to the gentle but persistent push of radiation pressure that so dramatically reshaped the path of their smaller brethren. Consequently, their trajectories deviate only minimally from the original cometary orbit. If the cloud of debris only begins to intersect the Martian hill sphere, the region of space where Mars's gravity dominates after the October 3rd flyby, then these larger fragments will be on a slower, more direct route to their eventual rendezvous. Their journey is governed purely by celestial ballistics, a predictable arc that delivers them later, but with far greater consequence. Why would the most substantial pieces, those capable of leaving a lasting mark, be destined to arrive last? The mainstream explanation is one of simple dynamics. In the zero-sum game of orbital energy, the small, light particles gain a velocity boost from solar radiation, allowing them to cut the line and arrive early. The larger chunks, devoid of this auxiliary propulsion, must follow the slower, Keplerian path. Scientists suggest this delay could be on the order of hours, or even days, creating a clear temporal separation between the harmless dusting and the potential for significant meteoritic influx. This staging of the event allows for a calibrated scientific response, a chance to observe the initial effects before the possibility of larger impacts. But does this clean, mathematical separation account for the potential of chaotic gravitational shepherding within the debris cloud itself? A more speculative view might consider the larger fragments not as isolated projectiles, but as the cause of their own miniature swarms. Each sizable chunk could be trailing its own halo of finer debris, a personal cloud of dust and gravel liberated by rotational disintegration or thermal stress. As these larger bodies begin their final approach, their gravitational pull, however faint, could focus and organize this trailing material. The resulting impact profile would not be a simple sequence of increasing size, but a series of clustered events, each centered on the arrival of a primary fragment. This would turn a steady rain into a series of localized storms. Furthermore, their immense mass makes them less susceptible to atmospheric ablation. While the tiny vanguard particles vaporize high above the surface, a centimeter-sized object could survive to penetrate deep into the stratosphere, and a meter-class object could potentially excavate a fresh crater on the ruddy soil. Could the most profound geological evidence of this encounter be delivered not by the first wave, but by the last? The evidence for this delayed procession is etched into the geometry of the flyby itself. Precise orbital calculations show that the highest probability for the larger debris to intersect Mars occurs not at the moment of closest approach, but along a subsequent arc of the planet's orbit. The comet and its major fragments will have swung past, and Mars will, hours or days later, journey through the debris trail they left behind. It is a cosmic meeting missed by a fraction of a celestial clock cycle, a delay written into the fundamental parameters of the encounter. Observatories across the inner solar system will be tracking the larger, reflective fragments, their paths predictable yet freighted with uncertainty. What unpredictable showers might they spawn in their final moments of descent? The implications of this sequenced arrival are profound for our robotic envoys on and around Mars. The orbiters, having studied the initial plasma and chemical perturbations from the dust, would then need to reorient their instruments to monitor the upper atmosphere for the brighter and deeper streaks of the larger meteors. Rovers on the surface, equipped with panoramic cameras, could be programmed to scan the skies during the predicted windows, attempting to capture the fleeting fireballs that would illuminate the Martian night. These would be the first such meteors ever observed from the surface of another world, a direct observation of cometary material sacrificing itself in an alien sky. What secrets of cometary composition could be gleaned from the light of those distant, silent explosions? Thus, the narrative of the cometary encounter unfolds not as a single act, but as a meticulously paced drama in multiple scenes. It begins with a cryptic, almost imperceptible overture of icy dust, a phenomenon that challenges our very methods of detection. This is followed by a long, uncertain intermission, a period of waiting and calculation. The climax arrives not with a bang, but with a prolonged, escalating series of deeper, more resonant events, as the larger and more consequential fragments finally complete their slower, more determined journey. Each wave tells a different part of the comet's story, from its most volatile ices to its most resilient rocky core. But if we can map this incoming tide of debris, from the smallest speck to the most substantial fragment, what then remains of the comet itself? This progression from micro to macro inevitably forces us to confront the ultimate source, the central enigma from which all this debris flows. The cosmos operates on a scale of forces that often defies our terrestrial intuition, a truth laid bare by the intricate ballet of cometary debris. As the fragments of comet 13P Olbers-Strecker dispersed along its trajectory, a curious dynamical segregation occurred. The smaller particles, mere micrometers in diameter, experienced the subtle but relentless push of solar radiation pressure. This force, proportional to a parameter known as beta, the ratio of radiation pressure to gravitational attraction, acted as a cosmic sieve. For these minuscule grains, beta was high. Radiation pressure became a dominant force, effectively reducing the sun's gravitational pull and accelerating them ahead of the main cometary nucleus. They were the lightweight sails caught by the solar wind, destined to arrive first. Conversely, the larger fragments, those ranging from centimeters to meters in size, possessed a low beta. Their greater mass rendered them largely immune to the photon's push, bound more tightly to the laws of pure gravitation. Their immense inertia acted as an anchor, causing them to lag behind the swift, dusty vanguard. If these substantial fragments were to arrive at Mars, their journey would be a longer one, their entrance into the Martian sphere of influence delayed by the very bulk that defined them. Could it be that the most significant arrivals are not the first but the last? This dynamical framework, supported by data from the coordinated tracking campaigns of ESA and NASA, places stringent constraints on the timeline. The geometry of the encounter, defined by the comet's perihelion passage in late October and its closest approach to Mars in early October, creates a narrow window. For a large, low-beta fragment to intersect the Martian Hill sphere, the region of gravitational dominance, it must have been ejected from the nucleus with a very specific and perhaps improbable vector and timing. The models suggest that such a fragment, if it exists, would not arrive with the initial cloud of fine dust, but would follow a more sedate, predictable orbit, its path deviating only slightly from the parent body. It is a prisoner of momentum, its trajectory a ghostly echo of the comet's own. So, if our sensors on the red planet remain quiet during the peak of the predicted meteor shower, does the true spectacle still linger in the deep, awaiting its moment? From this foundation in orbital mechanics, a more speculative yet captivating possibility emerges. Imagine not a shower of fine dust, but a solitary traveler. A fragment the size of a baseball, a classic dirty snowball of ice and rock, surviving the interplanetary voyage. Its path, dictated by the cold equations of celestial motion, is not towards the surface, but into a precise and rarefied corridor. As it enters the Martian atmosphere at a high velocity, it does not descend. Instead, it encounters the uppermost layers, the region where the atmosphere is just dense enough to generate immense frictional heat, yet too thin to cause rapid disintegration. This fragment would not create a shower of meteors, but a single isolated bolide, a brilliant, fleeting point of light, burning with an intense, white heat against the twilight sky of the Jezero crater. It would be a transient star, igniting and extinguishing in a matter of seconds, witnessed only by the unblinking eyes of our rovers and orbiters. What would such a solitary, high-altitude conflagration reveal about the structural integrity of cometary fragments that conventional models deem impossible? The evidence we must consider spans a spectrum of plausibility, demanding a tripartite analysis. At the first, most conservative level, we must accept the null hypothesis. No large fragments penetrate the Martian atmosphere. The cloud of debris is composed exclusively of fine particulates, creating perhaps a diffuse, the high-altitude haze detectable only by the most sensitive spectrometers on orbiting assets like MAVEN or the Trace Gas Orbiter. The sky above Perseverance would remain unchanged, the event recorded only as a slight perturbation in atmospheric chemistry. Is the absence of a visible phenomenon itself a form of data, confirming the purity of the cometary disintegration? The intermediate scenario introduces a layer of complexity. Here, a handful of larger meter-scale fragments, possessing a slightly elevated beta value, manage to arrive with the main swarm. They are not the laggards, but the median of the distribution. These would penetrate deeper, burning up as faint, scattered bolides. Their light would be too dim for the rover's cameras to capture clearly against the daytime sky, but a dedicated meteor sensor on the surface might register the telltale ionization trails in the upper atmosphere. This would align with standard models of cometary fragmentation, a gentle statistical tail on the distribution of particle sizes. But does a handful of faint streaks truly account for the full potential of a comet's disintegration? Then we arrive at the extreme, low probability, yet dynamically permissible hypothesis. A cluster of centimeter to decimeter fragments, the true laggards of the swarm, arriving hours or even days after the main event. Their high velocity and shallow entry angle would cause them to graze the upper atmosphere. The physics of such a grazing encounter is profoundly different from a direct impact. Instead of a rapid, catastrophic detonation, the fragment undergoes a prolonged, ablative burn, skimming across the top of the atmosphere like a stone across a pond. It would produce a short, intensely bright streak, a horizontal flash of light that vanishes as quickly as it appears. The atmospheric drag would slightly alter its orbit, casting it back into the void, a scorched and diminished wanderer. Have we, in our focus on direct impacts, overlooked the potential signatures of these atmospheric grazers? The implications of such an event, however unlikely, extend beyond mere observation. For the robotic emissaries we have placed on the Martian surface, it presents both a hazard and an unprecedented opportunity. A network of sky-facing sensors designed to monitor atmospheric opacity or seek out transitory clouds could be reprogrammed to act as a meteor early warning system. The detection of a single high-altitude bolide would provide a direct measurement of the flux and size distribution of the cometary debris. The spectral signature of its burn would offer a real-time assay of the fragment's composition, a pristine sample of a comet, analyzed remotely as it vaporizes in the Martian sky. Yet, the probability remains vanishingly small, a calculated risk in the grand experiment of interplanetary exploration. But if we do not watch for the improbable, how can we ever claim to have witnessed the truth of the event? And if such a fragment, a late-arriving messenger from the depths of the solar system, were to trace a fiery path across the Martian heavens, what preparatory signs might we have missed? What earlier, more subtle signal could have hinted at the water-rich nature of this incoming celestial body, a precursor to the potential spectacle of its disintegration? This very question finds a potential answer in the archival data from the Swift Observatory, from the months of July and August 2025. During two specific observation windows, the ultraviolet and optical telescope aboard Swift, known as UVOT, was trained on the approaching comet. The data it returned held a faint but critical signature. In the final days of July and the 1st of August, and then again in the middle of August, the ultraviolet spectrum of the comet exhibited a distinct rise in luminosity at specific wavelengths. This was not the broad reflected light of dust, but the sharper, more diagnostic emission consistent with the hydroxyl molecule, a known byproduct of the photodissociation of water vapor. The presence of OH is the ghostly echo of water itself, a beacon signaling that the comet's icy nucleus was actively sublimating, turning directly from solid ice into gas under the sun's increasing warmth. The mainstream interpretation of this data is straightforward. As the comet journeyed inward from the outer solar system, the intensifying solar radiation began to heat its surface. Ices, primarily water ice, started to vaporize, releasing gas and entraining the fine dust that makes up the comet's visible coma and tail. The Swift detections simply confirmed that Comet 13P Olbers-Strecke was behaving as expected, becoming active as it crossed the frost line. The timing and strength of the OH signal allowed scientists to model the comet's water production rate, a key parameter for predicting the density of the resulting dust tail. It was a standard calibration point in the lead-up to the Martian encounter. But does a standard interpretation fully capture the implications of this early water signal? A more speculative hypothesis begins to form when we consider the nature of this observed outgassing. The UVOT data did not show a steady, uniform release of hydroxyl, but rather hinted at possible variability, brief surges in the UV signature that suggested episodic jetting from the nucleus. This is not uncommon in comets. Localized pockets of volatile ices can erupt as they are exposed to sunlight. However, such instability is also a known precursor to fragmentation. The same pressures that build up to create a gas jet can, if sufficiently powerful, overcome the weak, gravitational, and structural bonds holding the nucleus together. The early OH signal, therefore, may not have been merely a sign of general activity, but the first indicator of the internal stresses that would later produce the very debris field we have been contemplating. Were we, in fact, witnessing the birth cries of the fragments whose journey we have just traced? This leads to a profound connection between the early ultraviolet data and the potential for late-arriving debris. The water vapor detected by Swift is the propellant and the glue for the cometary dust. The gas flow from the sublimating ice is what drags the dust particles away from the nucleus, populating the coma and initiating the formation of the tail. Without this gaseous release, the dust would remain largely bound to the surface. The presence of significant OH in late July and August confirms that the comet was not only active, but was actively building the dusty environment that would eventually sweep past Mars. The water was, in essence, priming the pump, creating the reservoir of material from which the larger, slower fragments could be ejected. Could the intensity of this early OH signal therefore be used to retroactively constrain the mass and number of those larger, high-inertia fragments? The detection of hydroxyl emission also serves as a crucial constraint for spectroscopic observations made during the encounter itself. Orbiters around Mars, such as the ExoMars Trace Gas Orbiter, or MAVEN, would have been watching the Martian atmosphere for any signs of cometary infusion. Their primary target would be the same hydroxyl molecule, which glows brightly in the ultraviolet when excited by solar radiation. If the comet's coma or tail directly interacted with the Martian atmosphere, even at high altitudes, it could leave a temporary, faint layer of water vapor or its dissociated products. The pre-encounter data from SWIFT provides the baseline composition of the comet's gas, allowing scientists to distinguish a genuine cometary infusion from background atmospheric processes. It is the before picture in a cosmic experiment. But if such an infusion were detected, would its signature match the quiet, steady sublimation of a stable nucleus? Or the violent, enriched outflow of a body in the process of coming apart? Ultimately, the SWIFT observations from the summer of 2025 act as a foundational chapter in this story. They transform the comet from a mere point of light moving along a predicted path into a dynamic, physically complex object. The faint UV glow was the first direct evidence that this traveler was carrying the essential ingredient for life, water, in vast quantities. It confirmed that the event was not just a gravitational alignment, but a chemical interaction waiting to happen. The water vapor and its hydroxyl tracer were the potential agents of change, the elements that could, even in the tenuous upper atmosphere of Mars, trigger a cascade of photochemical reactions. Did this early beacon of evaporating water ultimately foretell a more profound, yet unseen, delivery of volatiles to the red planet, a subtle rain of atoms from a passing ice world? The void of interplanetary space is not truly empty. It is a canvas upon which the fundamental forces of the universe paint with the most subtle of brushes. In the late summer of 2025, one of these brushes, the SWIFT Observatory, trained its ultraviolet and optical telescope on a seemingly inert point of light moving through the outer asteroid belt. What it recorded was not the reflected glow of inert rock and ancient ice, but the specific, telltale signature of the hydroxyl molecule, OH, at a wavelength of 3085 angstroms. This was the first spark, a phantom beacon flickering to life at a staggering distance of 3.5 to 2.9 astronomical units from the Sunday. According to current cometary science, such a signal should not exist so early in a comet's journey. Volatile ices like water should remain frozen solid, locked in a deep cryogenic sleep at these vast distances from the sun's warmth. The mainstream explanation posits that this could be the result of a population of highly volatile superices, such as carbon monoxide or carbon dioxide, beginning to sublimate, their energy indirectly catalyzing the release of trace amounts of water from the surface. But if the primary driver were carbon dioxide, why is the hydroxyl signal, a direct descendant of water photodissociation, so pronounced and persistent, while other expected spectral lines remain subdued? This early activation of the water cycle challenges the very thermal models we use to predict a comet's life. Could it be that the nucleus of Comet Swift is not a simple homogeneous dirty snowball, but something far more complex and engineered in its composition? This leads us to a more speculative hypothesis. Imagine if the dust grains surrounding this comet were not mere byproducts of sublimation, but sophisticated vessels. Each microscopic particle could be a capsule, a mantle of non-volatile silicate or carbonaceous material, acting as a protective shell for a core of pristine water ice. As the comet's journey brings it incrementally closer to the Sun, these capsules would experience a gradual, cumulative heating. Not enough to vaporize free surface ice, but perhaps sufficient to induce thermal stress fractures in their brittle shells. This would not be a steady outgassing, but a timed, punctual release, a microscopic carving of icebergs on a cosmic scale. The timing is what lends this idea its provocative weight. The initial OH detection occurred precisely as the comet's orbit brought it into a specific spatial relationship with Mars, as if the release mechanism was triggered not just by solar proximity, but by an impending celestial rendezvous. What if this was not a natural process of cometary decay, but a deliberate, timed deployment of a key resource? The data from the Swift-UVOT team, published in early August and early September of 2025, provides the empirical backbone for this event. Their papers confirm the detection of the hydroxyl radical on two distinct occasions, between July 31st and August 1st, and again between August 18th and 20th. This was not a single anomalous flicker, but a confirmed repeating signal of an active water source. Furthermore, the analysis indicated a measurable increase in the estimated water production rate between the first and second observing runs. The comet was not merely holding a steady state, it was becoming more active, its water output intensifying as it closed the distance, yet still remaining far outside the conventional zone of such volatility. The data is clear, but its interpretation remains shrouded in mystery. Does this increasing production rate signify a deepening fracture on the nucleus? Or could it indicate a cascading failure of more and more of these hypothetical dust capsules? To fully grasp the implications, we must analyze the phenomenon across three escalating levels of intensity. The first, and lightest, scenario involves only a subtle increase in hydroxyl ions within the comet's nascent, tenuous coma, a shroud of gas barely clinging to the nucleus. This is precisely what Swift observed from its distant vantage point. The second, moderate level, would involve a faint but detectable Lyman alpha glow in the comet's upper atmosphere. This specific ultraviolet emission, a hallmark of hydrogen atoms released when solar ultraviolet light breaks apart water molecules, could potentially be sensed by sensitive instruments in orbit around Mars. A faint ultraviolet aurora heralding the comet's approach. The third, and most extreme, scenario is one of pure celestial spectacle. It posits that the OH emission could become so robust that the comet's gas tail itself develops a weak, intrinsic glow. Under perfect conditions of a dark, twilight sky on Mars, a hypothetical observer looking upward might see this ethereal filament of light, a luminous thread painted across the heavens by the chemistry of disassembled water. Is such a visible manifestation merely a fanciful thought, or a predictable outcome of an exceptionally active and early-onset hydrology? The ultimate significance of this O beacon lies in its synchronization with other events. Its activation serves as a precise chronological marker, a T=0, for the comet's water cycle. By aligning this timestamp with the subsequent arrival of the comet's dust tail at Mars, we gain a powerful tool for forensic planetary science. We can begin to disentangle the separate roles of water vapor and carbon dioxide ice as the driving engines of the comet's activity. The water, announced by the OH signal, may be the primary agent for lifting and accelerating the finer dust grains, while carbon dioxide-driven jets could be responsible for ejecting larger, more massive particles. This O light illuminates not just the comet, but the very mechanics of its interaction with the Martian environment. As we stand at the threshold of this unprecedented encounter, we are compelled to ask, if this beacon is a deliberate signal, what message is it heralding? And what will be the consequence when this carefully timed release of water vapor meets the thin, waiting atmosphere of the red planet? But what happens when these exogenous particles, these travelers from a distant icy world, finally breach the defensive perimeter of a planet? The Martian atmosphere, thin as it is, represents a formidable barrier, a zone of interaction where chemistry and physics conspire to transform incoming matter. The MAVEN spacecraft, the Mars Atmosphere and Volatile Evolutio mission, has long served as our sentinel at this frontier, meticulously mapping the composition and dynamics of the Martian ionosphere. Its sophisticated suite of instruments is designed to detect the faintest whispers of solar wind and the subtle ballet of ions. In the days following the peak of the dust encounter, MAVEN's sensors will be listening for a new, distinct chord in this cosmic symphony. The mainstream scientific expectation is that the influx of cometary dust, vaporizing upon atmospheric entry, will inject a temporary, faint layer of metal ions, such as magnesium, sodium, and iron into the upper atmosphere. These ions, the atomic residue of vaporized cometary dust, should create a short-lived perturbation in the local plasma, a ripple that MAVEN's Langmuir probe and WAVES instrument and its neutral gas and ion mass spectrometer could potentially characterize. This would be a direct, in situ measurement of the comet's material fingerprint upon Mars. But is the story truly that simple? Can we be certain that the only interaction will be a passive chemical deposition of metals? A more speculative line of inquiry challenges this passive view. What if the cometary dust is not chemically inert? These particles have spent eons in the deep freeze of the outer solar system, their surfaces potentially acting as catalysts for complex organic chemistry, or even serving as substrates for unknown molecular structures. As they ablate in the upper atmosphere, they would not merely release simple metal atoms, they could unleash a cascade of complex ions and radical compounds. MAVEN's mass spectrometers would then not record a simple, predictable spectrum of common metals, but a chaotic, transient zoo of exotic ions. The plasma environment would not just be perturbed, it could become temporarily, profoundly altered, its electrical properties and wave behaviors shifting in ways that defy our current models of atmospheric physics. The ionosphere itself could become a natural cloud chamber, a vast laboratory for reactions we have never before witnessed. Could this artificial, temporary ionosphere hold clues to processes that once, billions of years ago, made Mars a different world? The optimal window for this detection is a narrow one, calculated to be a few days after October 3, 2025, when the orbital intersection with the comet's dust trail is predicted to reach its maximum density. During this period, MAVEN will repeatedly dip through the upper layers of the atmosphere, its sensors actively hunting for these faint, temporary signatures. The scientific value is immense. A confirmed detection of metal ions would provide the first direct measurement of cometary dust composition at Mars, validating our models of atmospheric influx. Yet, the greater discovery might lie in what we do not expect to find. An absence of signal where one is predicted would be equally profound, forcing a re-evaluation of the dust particle's size, composition, or structural integrity. A signal that is far stronger, more complex, or of a longer duration than anticipated would suggest that our understanding of cometary dust and its interaction with planetary atmospheres is fundamentally incomplete. Is MAVEN merely observing a meteor shower, or is it monitoring the inoculation of one world with the refined materials of another? The data it gathers will tell the tale of a meeting not just of two bodies, but of two entirely different histories of our solar system, and the silent, electrified chamber where they finally merge. What new state of the Martian atmosphere will emerge from this brief fiery interaction, and what will it teach us about the fragility and resilience of a planetary system? The solar wind, a relentless stream of charged particles, flows unimpeded through the Martian system, a stark contrast to the protective magnetic cocoon that shelters our own world. Here, the upper atmosphere, the ionosphere, is the planet's first and only line of defense, a fragile frontier where molecules are stripped of their electrons, creating a tenuous plasma. When an external force, such as a stream of interplanetary dust, breaches this frontier, the ionosphere does not remain passive. It responds. Data from missions like MAVEN, the Mars atmosphere, and volatile Evolutio N orbiter reveal that the system answers such an intrusion with a symphony of transient plasma disturbances, a subtle yet complex electromagnetic whisper against the solar gale. If dust and its associated ionized particles were to drift into this realm, what specific signatures would this delicate system inscribe upon the void? According to current models, the influx of fine particulate matter into the upper atmosphere would be a relatively benign event. The dust grains themselves, even if partially charged through photoelectric effects or triboelectric processes, would be too sparse to cause large-scale disruption. Scientists suggest this could lead to minor, localized increases in plasma density, a slight warming of the electron population as energy is transferred through collisions, a phenomenon MAVEN's sophisticated instruments are designed to detect with exquisite sensitivity. The expected signal would be a faint, statistical ripple in the background data, requiring careful filtering and analysis to separate from the normal solar-driven turbulence of the ionosphere. This is the predictable, quiet narrative, written by known physics. But what if the interaction were not so gentle? What if the introduction of charged particulate matter acted not as a simple irritant, but as a catalyst for a more profound and enigmatic phenomenon? We are compelled to consider a speculative hypothesis: the formation of a high-altitude, dry lightning. Not lightning as we know it, with thunder and water clouds, but a sudden, silent discharge of electrical energy triggered by the strange recombination of ions upon the surfaces of the incoming dust grains. These microscopic particles could serve as floating electrodes, facilitating a rapid and unexpected equalization of electrical potential within the ionosphere itself. Could such a process, invisible to the human eye, generate a fleeting cold fire in the Martian sky, a transient spark that leaves no burn mark upon the land but a distinct, if ephemeral, scar upon the plasma? The empirical data presents a puzzle that leans towards the subtle. The European Space Agency reported a crucial observation from its Mars Express mission. The CASSIS camera saw nothing unusual, while the MARSIS subsurface radar instrument registered a faint, momentary weakening of the overall ionospheric coma. This dissonance between optical silence and radio faintness is itself a profound clue. It implies that any cometary dust associated with Object 3, IATLAS, did not form a dense, reflective cloud, but rather a diffuse, electrically active stream. Consequently, if a signal were to exist, MAVEN would not have witnessed a massive ionospheric storm, but rather a pattern of small, fast disturbances, likely peaking a few days after the 3rd of October, when the geometric intersection with the dust stream was calculated to be at its maximum. The evidence, therefore, points not to a cataclysm, but to a ghost in the machine. What precise form did this phantom take? To comprehend the potential scope of such an event, we must analyze it across a spectrum of escalating intensity. At the first, most benign level, the interaction would manifest as a slight but measurable increase in the population of hot electrons, perhaps by a few percent. MAVEN's solar wind ion analyzer and Langmuir probe would register this as a minor perturbation, a gentle sigh from the ionosphere. This is the baseline expectation, the null hypothesis that conventional science would not find remarkable. But does a mere sigh account for the full potential of this celestial encounter? At an intermediate level of interaction, the anomalies would become more pronounced. We would expect to see clear variations in the local plasma frequency, a fundamental property dictating how radio waves propagate through the Brossa, ionized medium. Furthermore, spectrometers might detect the faint telltale streaks of metal ions, sodium, potassium, iron sputtered from the vaporized dust grains and immediately ionized by the intense solar ultraviolet radiation. These metallic traces would be the undeniable fingerprints of an external body having intruded into the atmospheric system. Their presence would confirm the physical passage of material, yet their ephemeral nature would raise a deeper question. What other, more transient effects might such an infusion of foreign matter provoke? The most extreme and most speculative scenario pushes the boundaries of our geophysical understanding. Here, the density of charged dust and the resulting ionization could be sufficient to form a temporary, localized conductive layer within the normally insulating upper atmosphere. This layer, a fleeting shield of its own making, could potentially deflect the magnetic field lines of the solar wind, creating a miniature, short-lived magnetosphere. For a few hours, a patch of the Martian sky might briefly mimic the protective qualities of a planet like Earth, rerouting the erosive solar wind around it. Is it within the realm of possibility that a cloud of dust could, for a moment, grant a dying world a temporary reprieve from its atmospheric execution? The implications of such detections, from the faintest electron sigh to the formation of a transient shield, extend far beyond a single event at Mars. They offer a critical lesson in exometeorology, providing a framework for forecasting microscopic dust storms around other weakly magnetized or unmagnetized planets. Worlds like Venus, or countless exoplanets orbiting active stars, may be subject to similar, frequent bombardments by interstellar or circumstellar debris. Understanding how the Martian ionosphere flickers in response to a dusting from the void teaches us the universal language of plasma physics in the absence of a global magnetic field. It is a masterclass in how a world, seemingly passive and exposed, can still muster a complex, measurable response to the gentlest of touches from the cosmos. But if the atmospheric response was so subtle, so deeply encoded in plasma waves and electron temperatures, what of the direct, visual evidence? Could any camera have glimpsed the source itself? This line of inquiry leads us inevitably to the perplexing silence from one set of eyes and the faint, yet positive signal from another. The overall brightness of the 3-eye Atlas object was calculated to be exceedingly low, far below the detection threshold for the cameras aboard Mars Express during its fleeting passage. The comet, or whatever it was, simply did not reflect enough sunlight to register as more than a few wayward photons against the overwhelming noise of empty space. It was an object defined more by its absence than its presence, a shadow whose properties had to be inferred from its effect on its surroundings rather than its direct emission. How can we study an entity that refuses to be seen? Yet, against this backdrop of optical silence, the color and stereo surface imaging system aboard the Trace Gas Orbiter performed a remarkable feat of astronomical perseverance. By stacking and processing a sequence of images, Cassis managed to tease out a faint, coherent signal, a visual thread where Mars Express saw only the void. This successful detection was not a portrait of a comet, but a critical upper limit. It placed a firm constraint on the density of large particles surrounding the nucleus. It told us what was not there, thereby illuminating what might be. The object could not have been surrounded by a significant cloud of dust or ice grains of a size that effectively scatters visible light. This contradiction in data between two capable spacecraft is not a failure of observation, but a refinement of the target's properties. It was small, dark, and carried its material in a form that was potent for ionospheric interaction yet feeble for optical reflection. So, if it was not a conventional comet, what manner of object, possessing so little light yet such a distinct electrical potential, was now receding into the darkness of the outer solar system? The Martian sky, a canvas of perpetual ochre and silence, is observed by two mechanical sentinels in a high, frozen dance. The Trace Gas Orbiter, with its Cassis camera, stares down with a patient eye, its exposure set to a deliberate 5 seconds. The Mars Express, in its venerable age, scans the same terrain with a quicker, more economical gaze, limited to a mere half-second. It is a difference in tempo, a variance in rhythm, that leads to a profound divergence in perception. The CASSIS instrument registers a faint, mobile point of light, a transient whisper against the vastness. The Mars Express, in that same moment, sees nothing but the enduring geology of the red planet. This is not a contradiction of data, but a revelation of method. The object, designated 3I Atlas, presents itself not as a solid beacon, but as a suggestion, its signal so tenuous that it only accumulates into visibility under a sustained and patient watch. Could it be that our very instruments, designed to capture the definite, are blind to the subtle? The conventional explanation rests comfortably within the realm of optical physics and engineering constraints. The CASSIS camera, aboard the trace gas orbiter, is a sophisticated imager designed for high-resolution color and stereo imaging of the Martian surface. Its 5-second exposure is a deliberate choice, allowing a greater influx of photons, amplifying faint signals that would otherwise be lost in the noise. The Mars Express, with its different suite of instruments and operational parameters, operates with a significantly shorter exposure time. From this perspective, the discrepancy is a simple matter of sensitivity. The signal from the comet was below the detection threshold for the Mars Express's imaging system at that specific moment. It was a whisper in a storm, heard only by the most attuned listener. The European Space Agency's clear statement that CASSIS acquired the faint, moving dot, while Mars Express did not, due to its half-second limit, seems to close the case with bureaucratic finality. But does a lack of evidence truly constitute evidence of absence? This leads us to a more speculative yet compelling hypothesis. What if the comet 3I Atlas is not merely faint but is partially shrouded? We imagine it not as a bare, icy nucleus blazing with reflected sunlight, but as an object draped in a diaphanous cloak of sparse dust. This would not be the dense, opaque coma of a typical comet near the Sun, but a tenuous, quasi-transparent haze of fine particles surrounding the nucleus. Under a brief exposure, this haze would be invisible, its light too dispersed to register above the background. It would be a form of cosmic camouflage, not by design, but by its intrinsic ethereal nature. Only under the prolonged integrating gaze of a 5-second exposure would these sparse photons be gathered and summed into a coherent, if faint, point. The Mars Express, blinking too quickly, missed the ghost for the machine. What other truths might we be missing by blinking too fast? The data from other instruments aboard these orbiters adds another layer of quiet mystery. The spectrometers Omega, SpyCam, and Nomad are designed to dissect light into its constituent colors, revealing the chemical fingerprints of materials they observe. In the first week of October 2025, their data concerning 3I Atlas was by all accounts inconclusive. The spectra were too faint, the signals too weak, to characterize the object's composition with any certainty. This aligns with the mainstream view of a distant, inactive, and therefore dim object. Yet, it also perfectly complements the speculative hypothesis of a dust cloak. Such a sparse cloud would produce an exceptionally weak spectral signature, one that could easily be lost in the noise of interplanetary space and instrumental limitations. The comet was not just visually elusive, but chemically silent. If it was speaking, were our ears simply not good enough to hear its language? We can analyze this enigmatic visibility through a tiered framework of escalating possibility. At the first, most conservative level, the detection was a matter of simple geometric positioning and instrumental capability. The CASSIS camera was pointed in the right place, at the right time, with the right settings. This is the baseline of scientific discovery, where preparation meets opportunity. It requires no new physics, only a competent application of the old. But is the universe always so accommodating to our established methods? At the second, intermediate level, we must ask what would happen if we were to push the existing data from Mars Express to its absolute limit. What if, instead of examining individual half-second frames, we were to co-add them? We would take dozens, perhaps hundreds, of these brief, empty exposures and stack them together, digitally aligning them and summing their photon counts. In such a rigorous composite, a pattern might emerge from the randomness. A faint, diffuse smudge, a hint of something that was there all along, might slowly materialize from the digital gloom. This would not contradict the initial non-detection, but would rather reveal the hidden information, the latent within it. The comet was not entirely invisible to Mars Express. It was merely subliminal. What other secrets lie hidden in our archives, waiting for the correct algorithm to bring them into being? The third, most extreme level of analysis projects forward to a time after the comet's perihelion passage. As 3I Atlas swings closer to the Sun, solar heating will intensify, potentially activating the nucleus and increasing its outgassing and dust production. Its brightness would surge. In this scenario, the tenuous dust cloak might thicken into a more traditional, brighter coma. The difference in exposure times between the two orbiting platforms would become irrelevant, as the signal would now be strong enough to saturate even the briefest of glances. Both the Trace Gas Orbiter and the Mars Express would see it clearly, a newfound consensus born from a change in the object's fundamental state. The initial discrepancy was not an error, but a preview, a measurement of the object's dormancy. Does the true nature of an interstellar visitor only reveal itself when it feels the touch of a foreign star? The implications of this photometric puzzle are profound, offering not just a mystery but an opportunity. It allows us to establish a crucial threshold for the object's brightness in its approach phase. The fact that it hovered just at the limit of detection for a 5-second exposure and below it for a half-second one tells us that the particle density in its immediate vicinity was exceptionally low. This is not the thick, churning cloud of an active comet, but something far more sedate and rarefied. For scientists running simulations of the comet's behavior and composition, this is a critical data point. It strongly suggests that models must prioritize scenarios where the coma is dominated by fine, sparse dust, a mist of microscopic particles, rather than a storm of gravel. This single observational discrepancy, therefore, calibrates our entire theoretical approach. But if the dust is so sparse, what force is gently lifting it from a nucleus that has known only the deep freeze of interstellar space for millions of years? This careful calibration of brightness and density naturally draws our gaze inward, towards the source of this tenuous haze, the nucleus of 3I Atlas itself. Here, we encounter a problem of fundamental dimensions. Our estimates for its size are frustratingly broad, spanning from a mere 300 meters to over 5 kilometers. This is not a margin of error, it is a chasm of uncertainty. The faintness of the signal allows for this wide range of interpretation. A small, relatively bright object could present the same photometric signature as a large, dark one. The precise nature of 3I Atlas remains shrouded within this ambiguity. How can we hope to understand the visitor when we cannot even be sure of its scale? The mainstream interpretation of this size range is cautious. It acknowledges the limitations of remote sensing. The albedo, or reflectivity, of the nucleus is an unknown variable. A dark, sooty surface would require a larger object to reflect the same amount of light as a smaller, icy one. Our telescopes measure flux, not physical diameter. Therefore, the wide estimate is an honest admission of this ignorance, a map that shows a vast territory of possibility with the label, "Here be dragons." It is a call for more data, for closer observation, for the refinement of models. But is this conservative stance preparing us for the true nature of this object? A more speculative hypothesis arises from considering the lower end of that size estimate. What if the nucleus is on the smaller side, perhaps only a few hundred meters across. This immediately introduces a fascinating and potentially dramatic implication: structural fragility. A smaller body, particularly one that has endured a long journey through interstellar space, subjected to unknown gravitational tides and cosmic radiation, may not be a monolithic chunk of ice and rock. It could be a rubble pile, a loose aggregation of fragments held together by the faintest of gravitational bonds. In such a configuration, even a moderate level of surface fragmentation, cracking and shedding, could have disproportionate consequences. The disruption would not need to be cataclysmic. The gentle pressure of solar heating as it approaches our Sun could be enough to trigger the release of a significant cloud of dust and small debris from a fragile, fractured surface. This moderate fragmentation would be far less violent than the complete disintegration of a comet, but from the perspective of a nearby planet like Mars, the effect could be substantial. The ejected dust, once liberated from the weak gravity of the small nucleus, would continue along the comet's orbital path, spreading out into a vast stream of particles. And Mars, waiting in its path, would find itself staring down the barrel of an unprecedented meteor shower. Could a seemingly minor event on a small distant rock precipitate a planetary scale event? This leads us to the final, profound implication. If the nucleus of 3I Atlas is small and prone to shedding material, then the quantity of dust it releases need not be immense to have a detectable effect. A relatively small amount of dust, when spread across the orbital path of a high-velocity interstellar object, could create a significant flux of micrometeoroids at the orbit of Mars. The planet would, quite literally, catch a rain of fine particles from another star system. Our models of Martian atmospheric chemistry and surface processes are built on an understanding of the local interplanetary environment. The introduction of an exogenous, interstellar component would be a watershed moment for planetary science. The MAVEN orbiter, designed to study the Martian atmosphere's escape to space, would suddenly find itself monitoring an influx from beyond. The inert sensors on the rovers would be pelted with dust not from the asteroid belt, but from the galactic void. Is Mars about to become a collector of galactic specimens? The indeterminate size of the nucleus, therefore, is not merely a technical inconvenience. It is the core of a deeper mystery. A large, stable nucleus suggests a predictable, if historic, flyby. A small, fragile one hints at a dynamic and ongoing interaction, a process of dissolution that could sprinkle the Martian environment with the raw materials of another planetary system. The faint optical signal that was seen by one camera and not another becomes the first clue in a chain of reasoning that leads us to question the very solidity of this visitor. We are left to wonder if we are observing a single, coherent body, or a fleeting cloud of debris that only momentarily holds the shape of one. As we watch and wait, one question hangs in the thin Martian air. When this object reaches its closest point to the Sun, will it reveal itself as a stone or as a shattering? The very nature of a cometary nucleus is to be an enigma, a world defined by its own transience. For the object designated 3I Atlas, this fundamental uncertainty is magnified, its core dimensions existing only as a broad estimate, a span from a mere 300 meters to over 5 kilometers. This is not a failure of our instruments, but rather a testament to the object's alien composition and behavior. When the size of the nucleus remains this ambiguous, every prediction regarding its structural integrity must be framed with profound caution, its boundaries stretched to accommodate a spectrum of possibilities. According to current models, a smaller nucleus would be more susceptible to complete disruption from rotational forces or thermal stress, while a larger one could harbor deep-seated volatiles capable of violent, localized outbursts. But what if the very concept of a singular, monolithic nucleus is inadequate for an interstellar visitor? What if we are not looking at a single body, but a composite? This leads us to a more speculative hypothesis. that the nucleus of 3I Atlas is not a simple homogeneous sphere of ice and rock, but a complex aggregation of multiple pieces, loosely bound together, a layered cake of carbon dioxide, water ice and dust. Such a structure, assembled in an unknown stellar system under conditions we can only guess at, would possess a geology of fragility. Each layer, with its distinct thermal conductivity and tensile strength, would respond to the sun's warmth not as a unified whole, but as a collection of individual entities. The carbon dioxide layers in particular would act as potent but treacherous engines. As the comet approaches its perihelion in late October 2025, the uneven heating, the cross-thermal stress could easily cause these vast, icy plates to delaminate and peel away from the core in great sheets. The data from coordinated observation campaigns by NASA and the European Space Agency already hint at this complexity. 3I Atlas appears potentially larger than its two interstellar predecessors, Oumuamua and Borisov, yet its diameter estimates remain frustratingly wide, from under a kilometer to several. Simultaneously, spectroscopic analysis of its coma reveals a surprising dominance of carbon dioxide. Both of these factors, a potentially large but uncertain size and a carbon dioxide-rich composition, directly impact the calculus of its fragmentation as it swings around the sunday. Could the very volatility that makes it visible also be the agent of its dissolution? To comprehend the potential fate of 3I Atlas, we must consider the analysis across three escalating levels of structural failure. The first, a mild scenario, would involve only the shedding of the outermost surface layers. This would result in a moderate increase in dust production, a gentle exhalation of material that would slightly enhance the comet's coma and tail, an event barely distinguishable from normal cometary activity. The second, a moderate scenario, envisions the separation of substantial fragments on the scale of tens to hundreds of meters. This would not be a mere dusting, but a literal breaking apart, creating an entourage of smaller nuclei trailing the primary body, a ghostly procession of shards following the same celestial path. The third, an extreme scenario, posits the catastrophic disintegration of the core into multiple subnuclei, a complete structural failure that would unleash a prolonged and intense dust plume, a cloud that could persist for weeks, masking the remnants within a veil of their own making. Where on this spectrum of self-destruction will 3I Atlas find its destiny? The implications of this fragmentation, however, extend far beyond the mere observation of a comet's demise. They touch upon the very interaction between star systems. If the nucleus proves to be smaller than our initial assumptions, yet remains abundantly rich in carbon dioxide, the consequences are paradoxical. A modest fragmentation event, a simple exfoliation of its surface, could be sufficient to release an immense cloud of fine dust particles. This cloud, propelled by the solar wind and radiation pressure, would not simply dissipate into the void. The orbital geometry of 3I Atlas is such that after its perihelion, its debris trail is projected to cross the orbital path of Mars. This presents a golden opportunity, a natural experiment on an interplanetary scale. The Martian atmosphere, thin as it is, would be bombarded by this interstellar micrometeoroid shower, particles born in another sun's nursery. Instruments on the orbiting satellites and the rovers on the surface could analyze the influx, measuring the composition, velocity, and density of this exotic dust, providing the first direct, in situ data on the dynamics of interstellar material. But what secrets would these grains, forged around another star, whisper to our instruments on the red planet? This potential for a dusty outburst is intrinsically linked to the comet's most distinctive chemical signature, a signature that paints its tail not as a fiery streamer, but as a cold, energetic engine. Near-infrared data from the James Webb Space Telescope and ground-based observatories have confirmed an unusual and profound abundance of carbon dioxide. This prevalence of a volatile that sublimes efficiently at the colder temperatures found between 1.4 and 2 astronomical units from the Sun makes 3I Atlas a peculiarly potent object. While water ice, the traditional driver of cometary activity, remains frozen and relatively inert, at these distances, carbon dioxide is already transforming directly from solid to gas with vigorous intensity. This is not a tale of fire, but one of cold, relentless production. This constant outgassing provides a persistent force, a potential fuel source for a more dramatic eruption. As the comet reaches its closest point to the Sun and its internal thermal stresses peak, this readily available reservoir of carbon dioxide could act as the propellant for a massive, directed outburst of dust, eruption whose trajectory, by fortune of orbital mechanics, seems poised to shower the Martian system. How can a substance associated with coldness become the architect of such a potentially violent and dusty spectacle? The vast, silent expanse of the outer solar system is a repository of frozen memories, and the object designated C. 2023. A1 was one such memory, stirring from its icy slumber. As it journeyed inward from the darkness beyond Neptune, the first whispers of its activity were not the familiar signature of water, the lifeblood of most comets, but something far more volatile. Data streams from the James Webb Space Telescope's NEOSPEC instrument, collected in the early autumn of 2025, at a heliocentric distance of approximately 3.3 astronomical units, painted a portrait of an anomaly. The coma, the comet's tenuous atmosphere, was dominated not by water vapor, but by carbon dioxide. The ratio was stark, unprecedented. Carbon dioxide to water measured at approximately 8:1. This was a cometary composition that defied the standard models. A world where a normally secondary actor had taken the lead role long before the curtain was expected to rise. Alongside the carbon dioxide, trace amounts of carbon monoxide and carbonyl sulfide were detected, all encased within a matrix of water, ice, and fine dust. This was not merely a comet, it was a specialized engine, primed for a unique kind of performance. What does it mean when a comet's heart is made not of water, but of carbon dioxide, awakening so far from the Sun's warmth? The conventional understanding of cometary activity places water sublimation as the primary driver. As a comet approaches within roughly 3 astronomical units of the Sun, solar radiation provides sufficient energy to transform water ice directly from a solid to a gas, liberating trapped dust particles and forming the characteristic coma and tails. According to current models, the dominance of carbon dioxide at such a large heliocentric distance is unusual, but not inexplicable. Carbon dioxide has a lower sublimation temperature than water ice. It can transition directly to a gas in the vacuum of space at temperatures far below the freezing point of water. Scientists suggest this could be due to a surface layer particularly rich in carbon dioxide ice, or perhaps a crust that has been previously depleted of its more volatile components, leaving behind a carbon dioxide-dominated reservoir. This early activity would generate a gentle, persistent outflow, sufficient to lift the finest, smallest dust grains from the comet's nucleus, creating a diffuse and tenuous dust halo. The coma would be cold, its dynamics governed by this slow, steady exhalation of carbon dioxide gas. But if the activity is so gentle and the coma so cold, how could it possibly generate the forceful ejector required to propel significant amounts of dust across interplanetary space? This is where the conventional explanation begins to show its limits, and a more speculative hypothesis must be considered. The very coldness of this carbon dioxide-dominated coma may be the source of its hidden power. Imagine not a uniform cloud of gas, but a population of microscopic carbon dioxide ice, grains, mixed intimately with the dust. These are not simple frozen lumps, they function as minuscule cold gas thrusters. When a speck of carbon dioxide ice, a microcryocapsule, is exposed to even the feeble sunlight at 3 astronomical units, it does not sublimate evenly. A localized thermal gradient can cause one side to vaporize rapidly, generating a tiny jet of gas. In the frictionless environment of microgravity, this jet acts as a micro-rocket, imparting a precise vector of momentum to the dust grain to which it is attached. This is not the broad, weather-like push of solar radiation pressure. This is a directed, mechanical process. Each microscopic grain of dust, adorned with its carbon dioxide ice coating, becomes a self-propelled entity. Could these countless invisible microthrusters be the secret engine of this comet, silently aligning their collective efforts along a specific trajectory? The trajectory, as fate would have it, was of profound interest. As the comet continued its inward plunge, reaching its perihelion in late October 2025 at a distance of between 1.36 and 1.4 astronomical units, the sublimation of carbon dioxide would have reached a fever pitch. The rate of gas production would no longer be a gentle whisper, but a roaring torrent. In this heightened state, the efficiency of the micro-rocket mechanism would be magnified exponentially. The gentle, persistent outflow of the outer solar system would transform into a series of vigorous, localized eruptions. The dust, once lofted gently, would now be accelerated with considerable force. Analysis of the dust tail's morphology suggests a 3-tiered progression of this process. At its most benign, the carbon dioxide outflow merely sustains a thin, sparse dust sheath around the nucleus. At a moderate level, it sculpts the dust into a broad, sunward-facing fan, a fan whose geometry appears calculated to sweep across the orbital corridor of Mars. But at its most extreme, the hypothesis proposes a cascade of pulsed carbon dioxide jets, creating sequential packets of dust, fired forth like barrages from a natural celestial cannon. What force of nature could choreograph such a precise and targeted delivery of material across the void? The result of this unique composition and proposed mechanism is a dust tail optimized not for the finest, micrometer-sized particles, but for larger grains in the sub-millimeter range. These are the pebbles and coarse sands of the comet, too heavy to be pushed significantly by light, but perfectly sized to be ballistically launched by the impulsive force of the micro-rocket jets. They become the prime candidates for a direct encounter with the Martian system. Their larger mass and momentum would allow them to survive a high-velocity intersection with the upper atmosphere, not simply burning up as meteors, but potentially depositing cometary material directly into the Martian ionosphere. This presents a singular opportunity to test the principles of beta meteoroid dynamics and atmospheric gas drag through direct observation of plasma trails and occultation data from orbiters at Mars. A cometary tail, engineered by carbon dioxide and propelled by its own icy volatiles, could be aiming a stream of primordial matter directly at a neighboring world. But if this stream is so targeted, so effective, what was the initial condition of the comet that allowed for such a precise and potent configuration? The integrity of the nucleus is the foundation upon which all this activity rests. A stable, singular body would provide a consistent source of volatiles and a predictable jetting geometry. Yet, the very forces that drive such vigorous outgassing are also the forces that can tear a comet apart. The immense tensile stresses induced by rapid rotation and thermal gradients can fracture a nucleus, creating new, fresh surfaces and dramatically altering its behavior. For C 2023-A1, however, the observational record up to the beginning of October 2025 tells a story of remarkable cohesion. Despite intense scrutiny by the world's premier orbital observatories and ground-based telescopes, no evidence of a macroscopic breakup was confirmed. The comet remained a single, albeit active, point of light. The images showed a condensed, bright core, a coma that grew in density and complexity, but no secondary condensations, no expanding cloud of fragments that would betray a catastrophic disruption. The activity was described as low level, and the imagery consistently pointed to a fuzzy, yet singular, source. The scientific publications and agency reports from this period unanimously noted the absence of confirmed fragmentation. How can a body, subjected to such intense internal and external forces, maintain its structural integrity while exhibiting such dynamic and escalating behavior? The mainstream scientific explanation points to the inherent strength of a well-consolidated cometary nucleus. It is possible that C-2023-01 is a monolithic body, a single, large chunk of ice and rock that has survived previous perihelion passages, its structure annealed by time and gravity. The observed activity, however vigorous, may be confined to specific vents and fissures, channeling the sublimating gases away without imposing catastrophic torque or stress on the entire body. The thermal waves penetrating the surface could be sublimating the carbon dioxide in a controlled, layered manner, like the slow burning of a fuse, rather than triggering a sudden explosion. Scientists would argue that the absence of fragmentation is the expected state for the vast majority of comets, and its confirmation here simply indicates a robust, if unusually active, object. The low-level outgassing and fuzzy appearance are entirely consistent with a comet that is still holding itself together, its internal pressures not yet reaching the critical threshold for disintegration. But does the absence of visible fragmentation truly equate to structural integrity? Or could the disintegration be occurring on a scale too subtle for our telescopes to resolve? This leads to a more unsettling speculative hypothesis. What if the comet is not coming apart in a single, dramatic event, but is instead undergoing a process of continuous, internal disintegration? The intense carbon dioxide activity, particularly the proposed microjet mechanism, requires a vast, accessible reservoir of volatile ice. This could imply a nucleus that is not a solid chunk, but a fragile, porous matrix. A rubble pile held together by the very ices that are now sublimating away. The absence of macroscopic splitting does not preclude a wholesale weakening of the internal structure. The comet could be hollowing itself out from within, like a termite-riddled tree that still stands tall, its outer shell intact, while its core turns to dust. Each microjet event, each burst of carbon dioxide gas, is not just ejecting dust, it is also excavating a tiny cavity, enlarging pores, and severing the delicate gravitational and chemical bonds that hold the matrix together. The comet may be maintaining its cohesive appearance not through strength, but through a uniform distribution of weakness. Is the apparent stability of the nucleus merely a facade? A temporary state preceding a more profound transformation that has already begun from the inside out? The silence from the depths of space offers no definitive answer, only the persistent, fuzzy image of a point of light holding its secrets close, a prelude to an uncertain future as it draws ever nearer to the fire. The image is a paradox, a whisper in the void that has silenced the cacophony of prophecy. As of the 9th of October, 2025, the object known as 3I Atlas persists as a singular, tenuous smudge against the cosmic backdrop. All predictions of a grand, theatrical disintegration have been halted before this stark reality, captured by our most advanced optics. There is no evidence of a macroscopic fragmentation, no telltale binary nucleus that would signal a catastrophic rupture. The comet, having weathered its violent passage around the Sun, continues its journey outbound, its structure apparently intact to our distant gaze. How can an object, subjected to such profound stellar forces, exhibit such a stoic, unified front? According to current models of cometary science, a comet nucleus is a fragile aggregate of ice and dust, a primordial relic held together by a tenuous gravity. The intense thermal stress experienced during perihelion can trigger outgassing jets that act like natural rocket engines, spinning up the nucleus and potentially tearing it apart. Scientists suggest that the absence of visible fragments could be due to a simple gradual dissipation. The comet may be shedding mass uniformly, a steady loss of fine particulates that creates a diffuse coma without the dramatic ejection of large kilometer-scale fragments. This would be the most benign interpretation, a slow and quiet fading into obscurity. But that does not account for the peculiar resilience of this interstellar wanderer, an object forged in an unknown star system under physics we can only hypothesize. What if the fracture is not one of scale, but of perspective? We propose a more speculative hypothesis. The nucleus is not shattering, but rather undergoing a process of microscopic, delaminative disintegration, an onion skin peeling. The core sheds not in monumental chunks, but in a cascade of microscopic failures, a slow-motion explosion where the constituent grains separate from one another without generating the large, reflective satellites our telescopes are designed to find. The coma we see is not merely gas, but a cloud of fine dust, a celestial smokescreen, obscuring a fundamental transformation occurring at the smallest scales. Could it be that we are witnessing, not a death, but a metamorphosis, one that occurs just below our threshold of resolution? The data from the critical period of the 7th to the 9th of October, 2025, provides a crucial, if ambiguous, testament. The European Space Agency's CASIS instrument aboard the Trace Gas Orbiter, tasked with a dedicated observing campaign on the 3rd of October, recorded only a faint, mobile point of light. Concurrently, the Mars Express orbiter, with its different instrumental setup and shorter exposure capabilities, failed to capture a definitive signal. This collective data points towards an object of exceptionally low activity, a weak coma, lacking the density and complexity that would betray a violent internal struggle. The synthesized reports from space agencies and science outlets on the 7th and 8th of October consistently emphasize the object's close approach, a mere 30 million kilometers, yet uniformly conclude with the absence of any confirmed, separate fragments. The evidence is defined not by what is seen, but by what is conspicuously absent. This leads us to a tiered analysis, a ladder of escalating possibilities. The first and lightest interpretation is that we are observing only a background dust event. The comet has settled into a state of quiescent outgassing, releasing a steady stream of fine particles that constitute the faint coma, with no significant outbursts or fragmentation occurring. This is the null hypothesis, the simplest explanation that aligns with the peaceful imagery. The second, intermediate scenario posits a small outburst, following perihelion. The thermal shock wave, traveling through the heterogeneous nucleus, may have dislodged a population of decimeter-sized debris. These objects, too small to be resolved from Earth, but numerous enough to contribute to the overall dust budget, would explain the coma's persistence without violating the non-detection of larger fragments. But what if the truth is more extreme? The third, most radical tier suggests the complete delamination of the outer shell. The nucleus is actively and systematically shedding its outer layers in a coordinated microscopic failure, a structural collapse that remains entirely beneath the detection threshold for macroscopic fragments. The entire body could be unraveling, yet from our vantage point, it appears as nothing more than a steady, enigmatic blur. Is the integrity of the nucleus an illusion, a collective agreement of scattered light that masks its fundamental dissolution? The practical consequence of this is a profound recalibration of risk for the Martian system. The probability of a large rock, a kilometer-scale fragment impacting the Martian surface, has plummeted to near zero. The dominant risk is no longer one of catastrophic impacts and planetary-scale seismic events, but something far more subtle and insidious. The primary hazard now appears to be a prolonged, high-altitude rain of ionizing dust. As the comet's diffuse dust trail, generated by this microscopic peeling, eventually intersects the orbit of Mars, it will inject a fine mist of high-velocity particles into the upper atmosphere. This presents not a threat of destruction, but a unique scientific opportunity. For missions like MAVEN, which studies the Martian atmosphere, this event transforms from a potential disaster into an unprecedented experiment. The spacecraft's sensitive instruments will be poised to listen to the whispers of this influx, to analyze the chemical signature of ionized metals and exotic ions being deposited from deep interstellar space. What secrets of galactic chemistry will be revealed in the faint electrified glow of the Martian ionosphere? This impending interaction, however, is not an immediate consequence of the close approach. The geometry of the intersection is a complex dance of orbital mechanics and solar influence. The dust particles, once liberated from the comet's weak gravity, do not simply follow its path. They are subject to the relentless push of solar radiation pressure, the beta effect, which acts as a constant, gentle force, altering their trajectory. The solar wind, a stream of charged particles, further sculpts this flow, particularly for the smaller, charged grains. This forces a critical question of timing. When will this diverging river of dust finally cross the orbital node of Mars? The window is not defined by the comet's flyby on the 3rd of October, but by the subsequent drift of its discharged material. Over the ensuing days and weeks, this drift will curve the dust stream, gradually steering it towards a point of minimum distance with the red planet, a convergence predicted to occur before the 30th of October. But can we accurately predict the arrival time of a cloud whose very composition and particle size distribution remains a mystery? The exact moment of this celestial rendezvous hangs in the balance, a function of forces both known and yet to be fully characterized. The celestial mechanics at play following the 3rd of October flyby present a geometry of profound subtlety. The high beta dust particles, their trajectories permanently altered by the relentless push of solar radiation pressure, have begun a slow, inexorable tilt of their orbital plane. This gradual precession is not a random drift, but a precise astronomical clockwork, one that is calculated to open a brief, transient window of nodal intersection with the orbit of Mars. The temporal boundaries of this window are constrained to a matter of days, perhaps a few weeks, centered around the 30th of October. It is a fleeting alignment, a celestial corridor that opens and closes with the silent precision of a vault door. According to current models of orbital dynamics and radiation pressure effects, this is a predictable, if complex, consequence of the initial conditions set by the flyby. The European Space Agency's analysis of the event, derived from velocity and angular data captured in the immediate aftermath, provides a robust foundation for these simulations. The geometry is clear, the clock is ticking. But does this mathematical certainty capture the full picture, or are we merely observing the first, most obvious layer of a far deeper cosmic process? A more speculative hypothesis dares to personify the forces of the Sunday. Here, the solar wind is not merely a stream of particles but a sculptor's hand, moulding the comet's vast dust tail into a sweeping curved structure, a celestial arch, a funerary bow. The apex of this bow, composed of the finest and most easily deflected particulates, is theorized to sweep past the Martian exosphere. The timing, as proposed by this idea, is unnervingly precise. It would coincide with the local Martian dawn, a period when the planet's ionosphere is at its most tenuous, its protective electronic blanket at its thinnest. This would allow the dust to penetrate to altitudes otherwise unreachable. The mainstream explanation would attribute any observed ionization to known meteoroid influx, a constant rain of interplanetary debris. Yet, the data from the Trace Gas Orbiter and the reported inadequacy of the Mars Express instruments to detect the phenomenon suggest something with a very specific optical density and spatial distribution. Could the solar wind be performing a more intricate function than we have ever given it credit for, actively focusing a stream of matter towards a waiting world? The empirical evidence, though nascent, begins to sketch the contours of this event. In October 2025, the European Space Agency confirmed the timing and angular velocity of the dispersing dust cloud through data collected on the 3rd. This was followed in the subsequent days by Popular Science reports that performed a crucial act of interpretation. They noted the event was too faint for MEX, but sufficient for TGO. This single datum is far more than a technical footnote. It serves to calibrate and constrain the very dust distribution models we are now using. It provides a critical boundary condition, telling us not just what was seen, but what was not, thereby defining the luminosity and particle density profile of the incoming stream. We are, therefore, not operating in a realm of pure speculation, but of guided simulation. The instruments have spoken, and their testimony points towards a real, measurable interaction. But what is the true nature of the signal that lies between the detection thresholds of our orbiting sentinels? Our analysis must therefore proceed through escalating tiers of possibility, each more intricate than the last. The first, and most conservative, suggests a simple minimization of distance. The central axis of the dust stream is projected to achieve its closest approach to Mars within a period of 3 to 7 days following the initial nodal crossing. This would be a period of peak density, where the probability of dust-giant interaction is at its highest. A moderate hypothesis introduces a greater complexity. The dust stream is not a monolithic entity. It is a bundle of countless particles, each subject to slightly different forces, causing them to drift out of phase with one another. This could result not in one, but in 2 distinct nodal crossings, a primary and a secondary event, a double pulse of infinitesimal precipitation separated by days. Yet, the most extreme interpretation draws from the language of optics and catastrophe theory. It posits the formation of a dust, caustic, a gravitational and radiative lensing effect, where the paths of the particles converge not into a broad stream, but a thin, intense sheet. The result would not be a gentle shower, but a sudden, razor-sharp slice of micrometeoroids, a downpour lasting mere tens of minutes, an event of startling abruptness and intensity. Are we prepared to observe an atmospheric phenomenon that operates on such a brief and violent timescale? The scientific opportunity is as transient as the event itself. The directive is clear: to schedule dense observation blocks for the MAVEN spacecraft, specifically its imaging ultraviolet spectrograph and neutral gas and ion mass spectrometer instruments, across the predicted intersection phases. Their mission will be to capture the temporal structure of this micro-rain. They will dissect the event, moment by moment, seeking the spectral signatures of ablated material and the ionization trails left in the upper atmosphere. The data returned will be a direct record of this intricate orbital dance, a testament to the gravitational and radiative forces that shape our solar system. It will tell us the when and the how of this particular interaction. But will it reveal the deeper question of why this specific alignment, this particular geometry, holds such significance in the broader narrative of planetary evolution? This meticulous planning for observation naturally leads to a more fundamental inquiry, one concerning the very sequence of arrival. As we prepare our instruments to witness this event, we must ask, what is the order of the procession? Which particles, dictated by the unyielding laws of physics, will be the first to make contact? The forecast suggests a hierarchy of impact, a structured sequence dictated by the interplay of radiation pressure and gas drag. The initial vanguard is predicted to be sub-millimeter dust, particles rich in volatile ices like water and carbon dioxide. Their high surface area to mass ratio makes them most susceptible to the radiative forces that have sculpted their path, propelling them ahead of their larger brethren. Following this initial wave would come the larger, more massive millimeter to centimeter-sized grains, their trajectories less perturbed, their arrival slightly delayed. Finally, and with very low probability, would come decimeter-sized fragments, lagging far behind. This predicted sequence aligns perfectly with established models of beta meteoroid dynamics. It is a rational, expected outcome. But is this the entire story? Could the chaotic environment of a dispersing coma introduce unforeseen variables, scrambling this seemingly inevitable order? The anticipation now shifts from the geometry of the encounter to the very nature of the impactors themselves, forcing us to confront the next critical unknown. The silent, tenuous atmosphere of Mars, a veil of carbon dioxide barely 1% as thick as Earth's, is not a place we associate with the fiery drama of meteor showers. Yet, in the latter half of the year 2025, our orbital sentinels began to record a sequence of events that challenges this quiet assumption. The data presents a curious, almost counterintuitive narrative of an influx of material from the interstellar visitor. The natural order of collision, as dictated by the physics of rarefied gas, suggests a specific hierarchy. The smallest particles, the submillimeter specks with high beta values, are the first to interact, followed by the millimeter and centimeter scale fragments, with decimeter or larger objects being a profound rarity. This is not merely a matter of size, but of momentum and susceptibility to the subtle but constant pressure of the solar wind. The smallest dust, possessing a high ratio of radiation pressure to gravitational force, is swept forward, a vanguard of finer material preceding any potential larger core fragments. Could it be that the very laws of orbital mechanics dictated that the finest dust from this object arrived first? A silent, invisible rain that our instruments detected only through its secondary effects? This established, scientific sequence, however, invites a more speculative interpretation. Imagine, if you will, not just inert dust, but an advanced swarm of luminous probes. Each minuscule particle, a high beta mote, could be seen as a scout, a forerunner. As these myriad specks encountered the upper fringes of the Martian atmosphere, they did not simply vaporize, they initiated a process. Perhaps their rapid deceleration triggered a subtle, localized excitation of atmospheric molecules, a faint, ultraviolet fluorescence, primarily in the hydroxyl radical. This would be the equivalent of a myriad of light-emitting insects, an army of mosquitoes, each seeding a transient, glowing trail, preparing the way, mapping the atmospheric entry corridors. This faint, widespread illumination would then be followed, days later, by the more sporadic and energetic entries of the larger, lower beta fragments, the large fireflies, igniting in brilliant but isolated bursts. The data from the James Webb Space Telescope and the Swift Observatory, confirming anomalous carbon dioxide and water activity alongside hydroxyl emissions in late July and August of 2025, provides a tantalizing, if circumstantial, backdrop for such a possibility. Why would the chemical signatures of disruption appear before the main event, unless the main event was not, in fact, the beginning? The empirical evidence began to crystallize with a specific observation. The CASIS camera aboard the trace gas orbiter managed to resolve a faint, moving atmospheric blur on the 3rd of October. This was not a brilliant bolide, but a subtle, elongated smear of light against the blackness of space. Viewed from orbit, its very faintness was the key. It provided just enough data to constrain the beta value models, strongly supporting the hypothesis of a size spectrum heavily biased towards small, fast-moving particles. The data, now part of the academic discourse on the preprint repositories, paints a compelling picture of a preferred size distribution where the small, in effect, went first. But does this observed preference for small particles truly close the case, or does it merely open a more complex chapter in our understanding of disaggregating interstellar bodies? Our analysis and inferences must therefore proceed through escalating tiers of possibility. The first, and most conservative level, posits a purely natural phenomenon. The high beta dust, a lightweight cloud of silicate and carbonaceous material, simply peppered the upper ionosphere. Its interaction would have been minimal, a gentle infusion of metals and a slight heating of the tenuous gases, an event detectable only by the most sensitive spectrometers and radio sounding equipment. This is the null hypothesis, the baseline against which all strangeness must be measured. It requires no new physics, only the straightforward application of known ablation and ionization processes. Yet, is the Martian atmosphere so easily perturbed, and do the observed hydroxyl plumes align perfectly with such a gentle, uniform influx? The second, intermediate tier of hypothesis introduces more energy and a greater diversity of material. To the vanguard of fine dust, it adds a population of millimeter and centimeter-sized grains. These are the lower beta objects, lagging behind their swifter, smaller kin. Their entry would be more dramatic, creating a series of faint bolides, meteors, too dim to be seen from the surface with the naked eye, but potentially within the reach of sensitive rover cameras or dedicated orbital imagers. These would be the sporadic flashes, the confirmation that the incoming stream contained a wider range of fragment sizes. The Cassis IS observation of the 3rd of October fits neatly into this intermediate model, representing one of these larger, but still modest, fragments. This scenario explains the temporal spread of events and the mix of chemical and optical signatures. But does the timing feel coincidental, a perfectly staged sequence from fine dust to visible meteors, or does it suggest a structured release of material from the source? This leads us to the third, most extreme speculative tier. What if the disintegration of the object produced not a simple cloud, but a structured, bimodal debris field? Imagine a double tail, not in space, but in time. A distinct, initial phase dominated almost exclusively by high beta, fine dust, creating a planet-wide, faintly glowing layer in the upper atmosphere. This would be the seeding event, the mosquito phase. Then, following a delay of 3 to 10 days, a second phase arrives, a sparser shower of lower beta, larger particles, the fireflies. The delay is critical. It is the time required for the solar wind and radiation pressure to sort the particles by their beta values, effectively stretching the debris cloud along its orbit. The hydroxyl formation, the anomalous water and carbon dioxide readings all precede the faint bolides because they are caused by the first wave, not the second. This extreme hypothesis forces us to reconsider the very mechanics of cometary outgassing. Could the process that ejected this material have been not a simple sublimation of ices, but a more controlled, layered disintegration? The ultimate outcome of deciphering this sequence is the solution to a fundamental inverse problem. By reading the timeline of events, the spectrum of activity across time, we can work backwards. We can infer the initial beta field of the ejected particles, which in turn reveals the physical conditions and forces at play during the object's close approach to the Sunday. Was the outgassing of carbon dioxide a violent, explosive event that threw off a wide mix of dust, or a gentler, more selective process that preferentially released fine surface material first? The answer is encoded in the arrival times of the different particle sizes at Mars. Solving this puzzle does more than explain a single event. It provides a predictive framework for the next interstellar visitor. If we understand how such an object behaves and disperses its material, we can forecast its interaction with a planetary environment. But what if the purpose of this precise sequencing was not natural, but designed a way to maximize atmospheric sampling or even delivery? The data stream continues, a river of numbers and spectra flowing from the silent red world. The initial phase, the rain of high beta dust, appears to be complete. The evidence for the second wave, the larger fragments, rests on a handful of faint orbital detections. The models are built, the hypotheses are laid bare upon the table of scientific inquiry. We have moved from the certainties of radiation, pressure, and ablation physics to the frontiers of speculation, where the line between a natural debris cloud and a purposeful, sequenced release begins to blur. The Martian sky has been subtly altered, its chemistry briefly perturbed by this encounter. As we turn our gaze from the mechanics of the influx to its ultimate manifestation, we must ask what traces this cosmic rain left upon the landscape itself, and what a hypothetical observer, standing on the rust-colored sands, might have actually seen in their sky.